Now, this is probably going to sound kind of obvious and a little bit silly, but common sense is actually a surprisingly powerful tool when applied to physics. There are many scenarios in which you can deduce whether your answer is an appropriate one, given that you know what you're looking for. First, I'm going to explain orders of magnitude. When writing in standard form, as you can see here, the number that 10 is to the power 2, n, is the number's order of magnitude. It's basically a very broad measurement of the number's size. So common sense in physics basically comes down to whether you think your answer is within a suitable order of magnitude compared to what you'd expect. There are some situations where it's hard to predict what the answer should be, but there are definitely a lot of areas where it's easy to deduce whether your answer is sensible. So let's take the ideal gas law, PV equals nRT, for example, where P is the pressure, V is the volume, N is the number of moles, and T is the temperature. If you've been asked to calculate the temperature, say, inside a balloon, one would expect the order of magnitude to be roughly about 1, so it would be within about 10 to 100 degrees C. Now, converted into Kelvin, that would be between about 283 and 373-ish. Because, I mean, you know, in the real situation of a balloon, it wouldn't really be realistic that the temperature would go any higher than, you know, the boiling point of water and any lower than, you know, reaching freezing. So it'd be somewhere in between. So in another question, you may be asked to calculate the number of molecules of gas there are in a tube or even a room. The number of particles in volume of gas is given by Avogadro's number, Na, which is roughly about 10 to the 23, and it tends to range between 1 and 100. That's the number of moles. It's about 1 to 100 for a general case. So a common mistake in calculations is missing a minus when writing in standard form, leading to unrealistically small numbers. If you find that the number of particles in any sensibly sized volume is anything less than an order of magnitude of 10, or even as high as 15, then it is likely a mistake has been made. An even easier mistake to find is if a number is actually found to be less than 1. So, for example, you've calculated the number of air molecules in a room and you find it to be 10 to the minus 23. Now, a mistake has been made here because 10 to the minus 23 is 0.000000023 onwards 0.1. That's a fraction. You can't have, if you're describing the number of things there are, then you can't have a fraction. So this is clearly wrong. In fact, the mistake that's likely been made is that you've accidentally divided by Avogadro's number rather than multiplied by it. So as you can see, you can just easily look at this answer and just think for a second and think, does this actually make sense? And, you know, if you have a fraction for the number of air molecules, of which there are probably about 10 to the 24 in a room, if you get something that is a fraction, then you probably wrong and probably made a mistake and should go back and see where you've done it. Now, one more small little example. The speed of light is 3 times 10 to the 8 meters per second. Now, a fundamental rule in special relativity is that you can't have an object moving at a velocity greater than the speed of light. So if you were to calculate the velocity of an air molecule, or even just the velocity of a car, to be greater than 3 times 10 to the 8 meters per second, then you must have made a mistake. Even without knowing this little bit of information, if you were given a question where you were calculating the speed of a car, then if you find that it's any order of magnitude greater than about 1, so about between 10 and 100 meters per second, then you've probably got it wrong, because once you get to about 1,000 meters per second, then you're getting into world record breaking, you know, feats here, and you probably made a mistake somewhere. So it's worth just thinking about whether your answer actually makes physical sense. You won't always be able to do it. Sometimes the answer will be a little bit abstract and it's hard to, give it some physical context. But actually, a lot of the time, you can think about it. Like, actually apply your answer to the situation and see if it makes sense. So I've shown how common sense thinking can be a good way of checking your answer, but actually it can be a good way of checking if your equations are correct. Dimensional analysis is perfect if you know the units of all the components of the equation, and I've explained that in another video. But it can sometimes take a long time to use, and sometimes you just don't know the units of one of your values. It can be sometimes quite hard to work out, especially if you don't have that number's value, say, at the back of your exam sheet that you can check. But you can still apply some common sense thinking. So let's take the example of momentum, which has mass and velocity in it. Now, I've written out what it actually is here, but say you were struggling to remember what it is, and you know it has mass and velocity in it, but you don't know how they're related to each other. Well, quickly using dimensional analysis, you should know that they shouldn't be added together, so it shouldn't be momentum is mass plus velocity, because that doesn't dimensionally agree. But you don't know whether you have to do mass divided by velocity or velocity divided by mass. Now, granted, again, you could use dimensional analysis, but I'm just using this simple example. Looking at this, think about what momentum is physically. It's almost like it's the oomph that an object has. It's the amount of weight it has behind it. So you should expect the momentum to increase as mass increases. And equally, you should expect it to increase as velocity increases. So that tells us that momentum should be mass multiplied by velocity, because as you can see in this equation, if you increase mass, then momentum should increase, and if you increase velocity, then momentum again should increase. So that's just a small thing you can apply just to check your equations are right. Instead of using dimensional analysis, which again can sometimes be a little bit complicated, just think, what does each term in the equation actually mean, and what happens if I were to increase it or decrease it, and what would I think would happen to the thing it's describing? So let's use another example. This is the equation that describes conduction heat transfer, where W is the rate of exchange of energy, K is just a constant that describes the conductivity of the object that connects these two objects at different temperatures. A is the cross-sectional area of what is connecting the two objects. This delta T here is the difference in temperatures, so T2 minus T1, and L is the length of the object connecting them. So let's analyse this equation and use some common sense. So we should actually expect more heat to be transferred at a time if we have a larger object attaching them, so one with a greater cross-sectional area. That means we expect A to be on top. You're multiplying by it rather than dividing by it, because that means as A increases, we expect W, the rate of change of energy, to also increase. It's the same in the difference in temperature. If you have a very large difference in temperature, then you have a greater amount of energy wanting to be transferred between the two objects. Whereas if they are the temperatures are close to each other and they're nearly the same, aka if the difference in temperature was 0, then we expect no heat transfer because they're in thermal equilibrium. They shouldn't exchange any energy between each other to get into thermal equilibrium. And finally, we have the length. The longer the distance between the two objects, the longer it should take to transfer energy. And that's reflected in the equation. We are dividing by L, so as we increase L, the rate of exchange of energy should decrease. Or, as we decrease L, so as we bring the objects closer, we should expect it to increase. So here I've just used kind of common sense thinking and just thinking like, right, how does each term apply to what I'm thinking? And you can you can make sure that you're getting it right. If I had K change in T over AL, so A was on the bottom, and I'd look at that and think, right, so if I increase A, the cross-sectional area of the connecting object, then that means that the amount of energy transferred will decrease. Well, that doesn't make any sense. So I hope you understand what I'm trying to get at here. So here I will be explaining how, again, you can use common sense, but using it to study the limits of an equation. So this is a slightly more complicated example, but let's look at this. We have a mass connected to two springs with spring constants K1 and K2. Now, the frequency of the mass oscillating in this system is root K1 plus K2 over m. Now, we can check that this is correct by considering a limit. So if we consider that K2 tends to 0, that means that the spring constant of that spring, if it tends to 0, that means it's not very springy. And as it tends to 0, it actually means that the spring kind of doesn't actually exist. It doesn't have any spring attributes at all. So let's look at this equation. If we were to make K2 tend to 0, that basically just eliminates K2 here, and it goes to root K1 over m. Now, actually, the frequency of a mass oscillating on a single spring is actually root K over m. And that agrees with what we've just shown. If the spring constant K2 tends to 0, then we've actually got a system where we essentially only have one spring. And the expression goes to root K1 over m, which agrees with what we expect if we have a single spring. So that's an example of using limits and common sense to check whether you've remembered the equation correctly. If instead we had, say, this as our expression that we've remembered it to be, then let's try it again. Let's imagine that K2, the spring doesn't actually exist, and make it tend to 0. Well, now if we make K2 tend to 0, then it actually makes the entire term go to 0. And that's not what we expect. We want it to behave like a single spring. So, again, so you can see how just using a bit of common sense and using these ideas of limits and just positing, right, so what do I expect to happen if one thing should go to 0, or if another thing should go really high compared to another thing? What should I expect to happen, and does this agree with my equation? So some of this, in particular the earlier points I made, may seem very obvious, but it is very easy to make a mistake and write an answer that you may not give a second thought. You can sometimes over-trust your ability to correctly type in your numbers into a calculator and come out with an answer that doesn't make any sense. But so many times people just trust that they have gotten the right answer, or they're not sure, but still don't think to actually study what they've got and see if it actually makes sense. So by practicing the common sense method, you can quickly gain a level of intuition that means you'll be able to recognise very quickly whether you've gone wrong and determine where it was that you did. Below you'll be able to find a few example questions that should test you on this topic. So I hope you found this helpful, and thank you.